I hope out of today you'll walk away with a couple of stories, a couple of threads, and one of them is a little bit about the history of Space Lab, how it got going, what the expectations were, what the realities were. So that's one major story. The other story is one that is about innovation. We're now in the new era. Somebody turned the key and we're going left instead of right. And innovation, breakthrough, et cetera, are languages that are terms that show up. I thought it'd be useful to try to use the story of CERC a little bit to talk about an instance of innovation as an example. So, there is this ongoing, I would say, legend that science and human spaceflight don't somehow interact well. And if there's anything that has strong opinions about it, it is that. There's a community, and you've heard from members of that community who have learned how to harvest tremendous value out of the opportunities that human spaceflight places in front of the science community. There are also those who feel very uncomfortable with sort of the environment and the infrastructure, and it's not like being in your own lab. You're not under, completely, everything is not under your control, and I think there are members of the community that feel very uncomfortable in an environment like that. But the clever ones, the ones who are innovative and can see opportunity, and there are many in the science community, I think, have learned how to take advantage of the capabilities that human spaceflight puts on the table. It's not the universal answer for all your ills by any stretch of the imagination, but it certainly does open up some doors that haven't been opened before, and I think what you'll hear in the next few minutes is an instance of that. So you might recall that the Nixon administration was approached toward the end, at the end of Apollo with some ideas for a combination of something like a shuttle and a space station. And the agency had to go through a great deal of pain and bargaining and interacting with OMB. Does this sound familiar? To find permission to get a go-ahead to build what is now and coming to unfortunately an end, the shuttle program. So there was, however, a little but attached to that permission. It said, okay, you want the shuttle, fine, you can have the shuttle. You want it so much, you got it. But by the way, you can't have any other launch vehicles to go with that. If that's the machine that's you want NASA, that's fine. But all these other rockets have got to kind of be put in the barn and forget about those. And so the agency actually agreed. And Lou Allen, who passed away not too long ago, one of my boss and the boss of many people in the Air Force for many years, was actually the person who signed on behalf of the Air Force that, yes, the Air Force would be using the shuttle for its launches. So there was now an expectation set that this very capable system, the shuttle, would be literally the universal answer for all your ills. All of those of you interested in expendables would be going up in the shuttle, and then of course the shuttle opens up doors to those who really wouldn't have an opportunity in an expendable flight system environment. European Space Agency signed on board, and their contribution was the Space Lab. And they had two agendas. Agenda number one was to learn about human spaceflight. And I'd say they accomplished that, very, very well. We have dramatic evidence, in the space station today. And agenda number two is they wanted to sell space labs because of the delusion, and we can only say that in retrospect, that there was going to be about a shuttle launched every week. If you miss the 147, I can get you on the 352 next Wednesday. 50 flights a week. That was sort of a year. That was sort of the basis, the flight model, and it was in that spirit that Office of Space Science went ahead and sent out a solicitation. AO 78-1, I think, was the the number, and got a huge response, many ideas about how to use the shuttle and to use the space lab. So now Europe was, I believe at that time, it was the biggest single international kind of a contribution in any engineering undertaking. It was really groundbreaking. So the space lab shows up, shuttle shows up. The flight rate, I came to NASA headquarters late in 1979. At that point, projections on the flight rate had begun to slope down fairly rapidly. By the time the shuttle actually started flying regularly, instead of roughly the projected 20 Spacelab flights a year, based on the 50 flights per year model, we ended up at around 6, and that number held 5 or 6, and that number held for a number of years. So flight rate versus the later realities was one of those lessons. It's not unique to the human spaceflight program. If you sit down, any group of folks planning a robotic mission, there's always this burst of excitement and enthusiasm, and we can do this, and then as the mission realities become apparent and the costs begin to climb, the scope begins to shrink until it finally asymptotically approaches what eventually ends up getting built and launched. So this isn't about a problem unique to human spaceflight. I think it's the character of all of us. We're engineers, we're scientists, we want to build things, we want to be successful, we want to show how we can make some changes on this planet. And I think that energy is really a huge asset for the agency. But this whole process of focusing on what eventually becomes real is an important thing to keep in mind. As the flight rate expectations and projections began shrinking, suddenly every mission became more and more precious. I mean, there's a supply and demand issue. And then as it became clear, I mean, the agency itself was learning. It was learning how to build the shuttle. It was learning how to fly the shuttle. It was learning what the good practices were. It was learning about the complexities of building payloads inside that environment, what was safe, what was not safe. So there was a whole body of experience and knowledge that was building up that eventually began surrounding the instruments and experiments that were flying, so that what was once advertised as we've got standard 19-inch racks, just pull it out of your lab, bolt it in, plug it in, and you're good to go. That story changed pretty dramatically with time. And that wasn't, I think, any ill will. I think that was a process of people just learning how this amazing system really worked, as opposed to the hopes and dreams in the early to mid 70s. So there was this whole gradual emergence of what is the reality of doing science inside the Spacelab environment. We also, Office of Space Science put together the notion of 3 test flights, Spacelabs 1, 2, and 3. And the principle behind those flights was to push the shuttle and Spacelab system to the maximum. So let's see, what's wrong with this picture? The first time you go up, you fly 50 experiments on 7 different disciplines just to test the boundary conditions on the first flight. Any problems with that approach? Well, of course, so Spacelab 1, while it became actually a landmark event because it accompanied, was the first flight of this major contribution by the European Space Agency, and it represented essentially heralding a new era in science. It was overly complicated. It should have been perhaps executed a little bit more the way an aircraft is tested. You start by just taxiing around the runway, taxi a little faster, then maybe you lift off a little bit, and you gradually expand the envelope. I think one lesson here was that there was too much built into the program too early. We executed the flights. They were in fact very successful. All the experiments got, I think, useful data, but the pain of integrating 52 experiments, both in a timeline as well as physically and testing them and validating them through the flow down in the O&C building. That was a major learning experience, and perhaps was pushing the system too hard too early. There was also the notion early in the program that since everyone's expectation was this was the universal answer to all your ills, that all sorts of experiments needed to fly. And in fact, on one of the space labs, Marshall, as I recall, put together a small cryogenic telescope just to test what was it like to do infrared astronomy from the shuttle. It turns out it wasn't that expensive an experiment, and it was a very important experiment to fly because it showed that the shuttle had around it a cloud of water vapor that basically blocked out infrared radiation up to around 100 microns. So that, in fact, was a successful experiment in the sense that it showed one of the limitations, and certainly didn't have to continue thinking about doing infrared astronomy from the shuttle. So that's an example, I think, of trying to force a science into an environment where simply, in retrospect, wasn't appropriate. But there are other sciences, and you've heard a couple of examples, and I'm going to give you one more, where you can actually exploit the human spaceflight system by simply respecting what it can do and paying careful attention to what it cannot do, and you can do absolutely amazing things. Another important lesson I think that we learned as the number of opportunities reduced, each flight became more and more precious, and more time and energy was spent to make sure that every experiment would be optimized. And as a result, there was sort of an ongoing push-pull between the community whose job was to protect the infrastructure, and the infrastructure in this case is the shuttle and the Space Lab system, and those flying experiments. So there was always a tension, I think, between those communities. And it was only, I think, as experience built up in the science community that became less of a problem, and that as the agency began to understand what really made sense to do in the shuttle and what didn't. There's also, however, an attitudinal shift that eventually broke its way, into this, and that was that those who were integrating the experiments had to take the attitude that their job was to help the PIs be successful instead of protecting the system from the PIs. And that was, it's perhaps a little subtle, but it's very, very important, and it makes a huge difference, I think, to the individual investigators to be able to interact with someone whose job is to help them be successful instead of the job is to protect the system from the principal investigator. The other problem, and I think we see this today in the station, is that the agency put stunning amounts of money into building the shuttle, building the infrastructure to support the shuttle, keeping the shuttle going, all appropriate. Same thing with the Space Lab. And then you compare that to the money that the country put into actually using them. I mean, it's hardly a balance at all. And here we see the same thing today with the space station. We have this incredible machine, $100 billion machine orbiting, and the uses, it's hardly used as compared to what its capability actually is. Just recently, Mark Uran sent out an opportunity, to the NASA centers to provide some ideas. I think he got 89 responses in the matter of a few weeks. There are plenty of ideas how to use the space station. But again, the resources that are available across the agency to put experiments into the station are extremely small, almost invisible by comparison to the resources available, necessary to keep the infrastructure going. So I happened to go by the Air and Space Museum by the Dulles Airport and found there the Space Lab. Those are my pictures. So there it is, unfortunately, resting in the museum rather than being actively used in the shuttle. But it's an important step, I think, in a learning step in the use of matching science undertakings with human spaceflight. So now let me talk a little bit about one adventure we've all had in using the shuttle. My boss, Charles Alachi, has a background as a radar scientist. In fact, he and a few folks were some of the first people to actually shine a radar from a rocket and look at the backscatter of the Earth. And that was done by a community of folks who thought radar could actually be useful as an Earth observing instrument. There are very, very few people who actually believe that. But like many investigators, you start with a rocket and a radar, and you get a minute or two of data, and then you take another step and another step. And that's a story I want to tell a little bit, because it slides right into what the shuttle and eventually what was done with the shuttle. So on the second flight, you recall that there were 4, call it test flights of the shuttle, after which it was declared operational and ready to rock. And on the second test flight, Charles, being a reasonably assertive man, found that the cargo bay of the shuttle was actually underutilized. It had in the back a very large, fairly complicated instrumentation. The vehicle had a lot of sensors built into it right in the beginning, just to understand how it responded in those during that engineering test flight period. So Charles was allowed to put together a radar made out of spare parts from CSAT, which was actually the first civilian radar in space. And he flew Sir A in the cargo bay of the shuttle in '81, and then in '84, and they flew twice in 1994. The idea being to look at the Earth at 2 different seasons. Originally, we actually had 3 flights to look at 3 different seasons, but again, economic pressure suggested 2 was pretty good. I think this may be one of the few things that has flown, like that twice in 1 year. And out of that was a mission that's actually a milestone mission. Not too many people really appreciate how profoundly the shuttle radar topography mission has affected all of our lives. So we went from a series of rocket launches back here in the mid-'60s, up into some aircraft. We flew CSAT, then Sir A on the shuttle, Sir B on the shuttle. There was then a more advanced radar that was put into to a DC-8 that actually the aircraft burned, as I recall, and the radar went with it, and then it got rebuilt. And it was sort of a laboratory test bed. In the meantime, right after 1985, after the first shuttle accident, we had started talking to the Europeans about a very elegant mission that is what became the SURC-XR joint mission. The Italians and the Germans combined to build the X-MAD-SAR. The US built the SURC, which was actually 4 radars, and flew twice in 1995. One of the interesting discoveries out of the early SARs, you might recall discovering a lost city in the Saudi Arabian peninsula, Ubar, was actually discovered by looking at imagery from the Sir B, I believe it was. Ubar happened to be noticed because the radar is very sensitive to texture. And in looking at the images of the Saudi Arabian peninsula, it was noted that there were many trails, many lines that seemed to converge on one spot. And that turned out to actually be the lost city of Ubar. The lines were camel paths that had been stomped over millennia, flattened, and the texture was very different from the surrounding texture of the terrain. And it turns out that frankincense is the sap, dried sap of a very unusual, scrubby-looking bush that is almost unique to that part of Saudi Arabia. And it just, it's an incense. And very, very, far more valuable than gold in the years before Christ. So there were trade routes established, and the city of Ubar happened to be sitting on in a water cistern, and was therefore a stop-off for the camel caravans. They eventually, Charles and some of his colleagues went, found Ubar. Turns out it had been missing because so much water had been taken out of the cistern that it collapsed, and half the city collapsed into this well. So this was one of the discoveries, one of the first discoveries, and one of the first signs that, boy, the radar is really a powerful tool. So these are just some images. This is Surrey being loaded in the cargo bay. And the other interesting discovery here was that people noticed, all these drainage channels in North Africa. And again, people trying to get some ground truth went there and said, there are sand dunes here. There's no stinking drainage channels. What's going on? Well, it turns out there were drainage channels. They were buried underneath the sand. And that's when people came to the realization that under certain conditions, mainly very, very dry soils, the radar actually penetrates. And eventually on Surrey, they put together a map of North Africa. They laid down, had enough data to put together a fairly thorough map, and there was a general sense that many of these drainage channels went east-west instead of north-south, suggesting maybe North Africa at one point had a tilt to it that it doesn't have today. Whoops. All right, so now here's just some imagery taken from Surrey. The radar is about the size of a Greyhound bus. Here is the X-band radar, which was produced by Germany and Italy. It was actually moved mechanically, like a aileron on a wing, and Surrey was a C-band and an L-band radar. Here are the big L-band panels, and here's the C-band panels. And so we were flying basically 3 different frequencies. X-band steered mechanically, and the Surrey radar steered electronically, so we could sweep the beam by just adjusting the phase of the various amplifiers in the radar. Oops. Just to give you a sense of the scale, this was what was in the cargo bay of the shuttle up here on Surrey. And now let me spend a few minutes talking about an aha. So Surrey flew very well. In fact, it flew well enough so that some of the mission team were starting to get a little bit bored. They were wandering, one of them, an engineer named Ed Caro, who was one of the engineers that helped Charles on his first rocket radars, was wandering around the halls of Building 30, and he saw a model of the space station. And he started looking at that model, and he said, you notice the mast that was now used to fly the solar arrays on the station. And he asked around and said, who's in charge of those masts? And some people eventually pointed him to someone, and he asked, gee, are there any spares of that mast around? And the gentleman said, yeah, we've built 11 of them. A couple are, have been tested to death. But yeah, if you promise to return it, we could probably make one available. We only need so many for the station construction. So Ed's idea was to convert the Surrey radar into a radar interferometer. What that means is that you basically send a radar pulse out from the main radar here, and then you receive that pulse by that radar. That's just the way Surrey worked. But then you build another antenna out here that also receives the pulse. And between the two, you basically have a radar interferometer. And with a radar interferometer, you can now do topography of the Earth. So Ed's idea was to take the X-band radar and stick it out here at the end of a mast. And he found a mast from the station that he could use, and so he was thinking during the course of the mission, well, so here's this kit. This is the next flight of this hardware. So we get back to the lab, radar returns, and we started looking at what one could do with such a radar. And the answer was, well, the X-band radar, it's high frequency, has a very narrow beam, so you could, in the course of a shuttle mission, wind sort of a spiral pattern. The ground track would be sort of a spiral pattern around the Earth, but you couldn't get global coverage. And the science community said, well, fun thing to do, but what's really important is global coverage. So, idea number 2, one of the team members, a scientist named Mike Kobrick, said, instead of using the X-band, let's use the C-band radar. And he had done a simple, little bit of geometry and discovered that operating in one of the particular modes, the electronics scanning mode of the radar, at an altitude of 233 kilometers, he would just cover the entire globe from 57 north to 60 south with the C-band. And so that's wow, that was a gift from heaven. That was a great idea. Now we needed a customer. So a gentleman named Nevin Bryant had been working for one of the other government agencies at JPL called the Defense Mapping Agency. And the Defense Mapping Agency had been for decades been trying to get a topographic map. I mean, you can imagine the Department of Defense has to be able to fight a war any time, any place, and was having a lot of difficulty getting a good topographic map of the Earth. So Nevin called some of his friends in the Defense Mapping Agency and said, hey, would you guys like to have a topographic map all done in 11 days with the following kind of metrics on its quality? And you could just about hear the cheers from California. They happen to be located near Washington. So they were very, very excited. In the course of 18 months, went from an idea to all the approvals through the entire Pentagon and the 4-star commands to actually get the money set aside. So we then showed up with NASA with a check for $150 million, a radar that had already flown twice, and a design for an extension of that radar that would turn it into this fairly amazing instrument. And a year and a half after that, we actually got approval to fly it in the shuttle. So this third kind of unexpected innovation-driven flight of this radar has really given all of us now a data set that has been desired, sort of the dream data set for many, many years. When you go to Google and you ask for a topographic map of something, you're seeing actually SRTM data. And you can go to the USGS data center in Sioux Falls, South Dakota, download as much of it as you want. And the Department of Defense has been using it. I mean, literally, they were pulling data out of our hands because at that time there were several bad things happening in the Middle East, and they put that data set to use virtually instantly. So here is a confluence of some things that resulted in a product that was just enormously useful. And I frankly don't think that the shuttle has been given, I think, the kudos, the shuttle system and the teams that support it, the appropriate kudos for enabling this marvelous achievement. Whoops. So this is some of the imagery. This is the boom in the canister that was bolted on the end of the radar. By the way, this as an example of, I think, how to go about doing something like this. You look at a 200-foot mass sticking out the side of the shuttle, and you wonder, what are these people thinking? I mean, that must be, that'll never get past the safety board. But as it turns out, we had flown twice on the shuttle. We called down to JSC and we said, hey, could we have an informal level double lot review of this? Just us boys around a table with this idea. And if it's a crazy idea, if you think it's nuts, we'll go home quietly. But if it isn't, could you give us some advice on how to make this a flyable system? A system you would feel comfortable flying. And that one meeting was I think, a tide turner, because they said, hey, no problem. This looks very, very cool. Just rig this so that if you push a button, it goes away. And that made sense. And so we spent a lot of time and energy making sure that there was a button in the crew cabin and the right pyros so that if this thing, for some reason, didn't retract inside the mold line and safe itself, we could get rid of it. And that simple advice, I think, was almost enabling for this mission. So you can see many of these scenes. Here's the San Andreas Fault, for example. Just very vivid, when you look at it as a 3D topographic projection. Many places around the globe. Here is the Chicxulub impact crater, which is actually buried under 500 feet of sediment. But you can see an outline of it, kind of a little indistinct, but there is an outline, and that outline is actually the result of springs that are ebbing up from sort of the lip of the crater, because the lip of the crater is only about 500 feet below the surface of, it's only got about 500 feet of sediment above it. This is all that remains of SRTM. It's also hanging in the Air and Space Museum. And this is the product of that mission, 1.5 terapoints of topographic information, each point being about the size of a baseball diamond. And so the entire planet, as you see here, has been broken up into baseball diamond-sized patches, and we know the altitude of each patch to an absolute accuracy of about 3 meters. It's a really remarkable data set. So just to wrap it up, bottom line, early expectations can be misleading. Again, it's not unique to human spaceflight. It's true also in robotic spaceflight, but in planning missions and thinking ideas, one's got to get real fairly fast, or you're going to waste a lot of time and energy. There are folks who have, I think, been extremely successful in exploiting human spaceflight flight opportunities. They do so by understanding, what they're flying in. They really need to understand the context in which the hardware is flying. The systems they build ought to be maximally self-reliant. Don't tax the human spaceflight with systems to do a lot of things that aren't absolutely necessary. Leverage the presence of human beings, and then also respect the presence of human beings. Make sure that what you're building is a reasonably built. And there are enormous capabilities that clever people can leverage. It also requires tenacity. Typically in Space Lab, an investigator would spend about a year of his career or her career for every day they got on orbit. That's sort of a sobering number. Also the notion that really the systems need to mature before you exploit them. Take it a step at a time. And if you do things right, the potential is absolutely amazing. It just requires ingenuity. So, questions?